minutes.
Okay.
Yep.
Wait, I guess it must be some kind of lag because, oh no, that's just saying when my lecture notes started.
So do you want us to help you keep an eye on the chat?
Yeah, I don't
okay?
see, I mean, maybe it'll pop up, but right now it's not showing. I mean, it might be that if somebody chats me, it pops up. But it's just, it's like a weird setup. Weird.
One of the students helped test it out. Did you see that?
No. What, if I find the little window, nope.
Yeah,
okay.
the text is a little blurry now for some reason.
Oh, do you think we should go back to the other approach?
Yeah, maybe let's switch back to the other approach.
Okay.
I'm not so we'll count it as a failed experiment.
Okay, we'll try it. Oh, sorry, it's not lecture 3 though, it's lecture 2.
Okay, so I think people are starting to sign back in. So we welcome Marilena again for her second lecture on cosmology. So whenever you're ready, you can get started.
Okay, great, thanks. Thanks a lot. So today we'll continue where we left off yesterday in this introduction to cosmology. So we were just, at the end of yesterday's lecture, we were just starting to discuss what I call the smooth, homogeneous, but also, I guess, average, let's say. I'm calling the average properties of the universe. And I had, so under the assumption that the universe is statistically homogeneous and isotropic, the line element can be written as in the FRW form. So there exists a coordinate system where the metric takes this form. And you can tell your friends on the other side of the universe how to get to this coordinate system because it's the one where everything looks homogeneous and isotropic and they don't see any bulk motions of stuff. So this is our line element, and then I'd introduced sort of two measures of distance, the physical distance interval, or the proper distance, which is the distance that we measure if we put down a ruler and measure intervals in space, or if we infer the distance by sending photons back and forth. That's the physical distance. I'd also introduced, so physical, and it's often called the proper distance. I'd also introduced the co-moving distance, which is not the one that we measure, but is the way that we measure the separation between points on a coordinate grid that we set up in the universe. And that is the distance, the spatial distance given by this piece of the metric right here. Now, we can make more sense out of this by noting, of course, that light and massless particles travel on paths with ds squared is equal to 0. And so if, for instance, on a radial trajectory in this universe, we could, that means that the relationship between the distance that particles can travel and the time that they've been traveling can be inferred from just setting ds squared is equal to 0. And then you have dt over a of t is equal to dr over 1 minus kappa r squared square root. And so this gives some relationships. So let's define the following. H, which is A dot over A, where dot is d by dt. So this is the Hubble parameter. And we'll see shortly that this can be rewritten as a function of A. So we can write it like this, and we can write, we can consider h to be a function of t, or in fact, h to be a function of A itself. We continue with our convention that A is equal to 1 today, and then we can compute the distance out to different, out to the universe when it was smaller. So at different values of A in the past. So, so let's see. So for instance, a photon with a redshift z that we measured, pulling 1 over A minus 1, has traveled a distance. We can compute the distance it has traveled to reach us. By just equating the sides of this. So using this expression up here and just rewriting things in terms of h, A prime squared A prime, and this can be written as dz prime over h of z prime. So we want to compute the distance that it travels. So say this is r0, and these are all r primes, and it travels from some value A to today, or is emitted when the universe is smaller by this amount, and therefore when we observe it, the wavelength of the photon is stretched by this amount z, it will have traveled this far. And the quantity on this side, we can write as chi of z or chi of A, and this is the coordinate distance. Sorry, this is let me just call this a distance. In a flat universe, this is also the co-moving distance. So sometimes this is called the co-moving distance. Also, and it's the exact same thing as the co-moving distance above if the universe is spatially flat. But the key point is it depends on the expansion history via this dependence on A right here. So you can integrate both of these. This one is arc sine of square root of kappa times r over square root of kappa. And so this gives distances, excuse me, excuse me, sine of square root kappa, not r, but chi of z over square root kappa for positive kappa. It just gives chi of z for kappa equals to 0, and it gives hyperbolic sine of square root of minus kappa for kappa less than 0. Okay, so if you know the expansion history, then you can compute the co-moving distance that a photon has traveled, say, since it was emitted until it reaches us today. To very good accuracy, we live in a universe that is spatially flat, and so we don't have to worry about these sine and sinh functions, and we can be sloppy about calling this function chi is also the co-moving distance, so that's fine, but it's good to know. So distance measures in cosmology that we use. So up here I said that the distance depends on the expansion history. So conversely, if we know the distance in the redshift, then you can reconstruct the expansion history. If you measure multiple distances in redshifts, you can try to reconstruct the expansion history. And there's a set of sort of distance measures that we use. So I already introduced the co-moving one, which is just a helpful theoretical toolkit. And objects at rest with the expansion have fixed coordinate distances. There is the proper distance, which depends on the time that you're looking at. So when the universe has scale factor A, or redshift Z, and we can write D proper is equal to A times R of A kappa. The ones that astronomers measure have other names. There's the angular diameter distance. And so this is, you know, as I said before, we're stuck here on Earth, so we just look out and we can't go out and see how far apart things are in the universe and measure that as a function of time. We can just look at like angular sizes of things. Now, if we measure the angular size of an object and we know its actual physical size, then you can infer the distance to it. So the angular diameter distance, to an object of known size L with observed angular size theta is dA is equal to L over theta. And if you work out what this should be by just drawing a diagram on some coordinates, you'll find that this is actually the same as the proper distance. The luminosity distance is another distance measure that's used in cosmology. So this is the distance to an object of known luminosity with an apparent flux measured here. Then the luminosity distance is the distance that you get by assuming that luminosity falls off as 4 pi d squared. So if you invert that, then you get this. If you compute this, this is dA over A squared, or in terms of our co-moving distance, it's R over A. So these are things people measure. Then there's this clear relationship that dL should equal dA over A squared. So let me add the arguments here. This is called the distance. It's called something like the distance duality relation. And you could check it, for instance, if you were using type 1a supernova to map the expansion history of the universe, and you want to make sure that there's not something else that's attenuating the flux of those photons, like scattering off dust or converting to axions or whatever, you can check whether the angular diameter distance that's measured in galaxy surveys agrees with the luminosity distance to this relationship. And at present, there's no known violations of this distance duality relation. Note that everything I wrote down so far holds. I haven't really assumed GR yet. I've just assumed metric theory. So even if the metric solves some other more complicated equations, like some modified theory, all of this distance stuff, the trajectories and so on, this stuff all still holds. It doesn't depend on GR. I haven't imposed Einstein's equation. Okay, now we're going to impose Einstein's equation and see how this function, what the dynamics of this function A of t are. So we add this So we have the equation GAB equals 8 pi G TAB, and we're going to plug in our FRW metric. Now, up here, I use the FRW metric in spherical coordinates, but now I want to just be a little bit more general, so that you could use Cartesian coordinates or whatever you want. So I'll write the form of the metric in a different way, which is ds squared is equal to minus dt squared plus a squared of t gamma ij dx I dxj, where this gamma ij is the maximally symmetric 3 metric for spatial hypersurfaces. And so for instance, it's just the Kronecker delta for kappa equals 0 for flat. And delta ij is independent of t. Okay, so now we want to compute the left-hand side of this equation. So first we compute the Christoffel symbols really fast. We can use this. So this is the formula for computing the Christoffel symbols. And if you plug in this metric right here, it's pretty simple, and life is good in our homogeneous and isotropic universe. Oh, maximally, sorry, there's a question. What does maximally symmetric mean? I'm not defining it here, but it means that this metric possesses the maximal symmetries of a space-time of this dimension. And that will, if you haven't had general relativity, don't worry about it. It just means, for our purposes, it means that I can write the curvature in a very, very simple form, which might actually become a little bit more clear. So the fact that this is maximally symmetric will turn out to mean that this metric, so it doesn't depend on time, of course, and then there's just this one parameter that determines all of the geometry of these spatial slices, and that one parameter is the spatial curvature. And so that means that when you compute the spatial curvature, it's just that number, and if you compute the curvature, higher order curvature tensors, they all just depend on that exact same number. But if that's confusing, don't worry about it. It's not really relevant. It's just to know. I mean, we won't need any details about that. Okay. So these Christoffel symbols all vanish. The only non-vanishing ones are these ones. The ones, these with mixed spatial indices. This one, and let me write these all just to be super clear. So this Christoffel symbol is an object that is symmetric in the lower two indices. So that's why I don't have to write all of these separately, but I will. And then the spatial ones, the Christoffel symbols that are all spatial, I'm not going to bother writing out because I haven't specified the coordinate system I'm using for gamma ij, but I'll just call this this gamma tilde, where this means the Christoffel symbol for this metric. So that means take this exact same formula, but only instead of plugging in the 4D metric g mu nu, you just plug in a little gamma everywhere. But we can write everything just in terms of these for now. Now, since gamma ij is maximally symmetric, Then the Riemann tensor for that space. So again, the Riemann tensor just for the gamma ij metric takes a simple form, which is spatial curvature, and the rest is just proportional to these metrics. Okay. Okay, so now we can compute the components of the Richie tensor. So GAB is equal to RAB minus 1/2 RGAB. So we need first the components of the Richie tensor, so, which is for the GR newbies, that's just this one with 2 indices here. And this one is can be rewritten in this way. It's pretty simple. Let's see, I don't have enough space here. Well, let's see if I can typo. Sorry, this is a double dot, that's A, and this is 2A dot squared gamma ij. So the space-time curvature R is given by contracting that. So this is space-time curvature. So even if kappa, the spatial curvature is 0, the space-time curvature is not 0, as long as this function A is changing with time. So for a Minkowski metric, right, this A would just be some constant, and so the space-time curvature clearly vanishes. But in our case, it doesn't. Okay, so we can keep going with this and compute the components of the Einstein tensor. And we will spare you some algebra. This is simple. So the A double dot terms cancel, and you get 3A dot squared over A squared plus 3 kappa over A squared is equal to G00, 0. And so this is going to give us our first equation, which we can write. We have this, we know, is equal to 8 pi G T00, and this is just the energy density of all the stuff in the universe. So we can write this as A dot over A squared plus kappa over A squared is equal to 8 pi G over 3 sum over X, rho X, where this is energy density of stuff X. So the universe has a bunch of different things in it, and we have to add it all up. This is often also written in the form using that H term that I introduced earlier, sum over X, rho X. And this is the Friedmann equation. The mixed space-time components for this symmetric universe don't give anything. This gives 0 equals 0, so we get no new information from there. The spatial ones, Gij equals 8 pi G Tij, do give us some stuff. So now we have to compute Gij from everything we have earlier, and we will find it is R tilde ij plus A double dot A plus A dot squared gamma ij. So this is Rij. And then we subtract A squared over 2 gamma ij times the spatial curvature, which we computed above, 6 A double dot over A plus 6 A dot squared over A squared plus 6 kappa over A squared. So this is and let's see, we know our tilde ij is 2 kappa gamma ij. So we get Gij is, let's see, okay, good. Wait, am I missing a factor somewhere? 2. Oh no, there's this 2 here. So that, okay, so we get 3, right, good. So we get 2 kappa from here, and then we subtract 3 kappa gamma ij from there. And so we get minus kappa. Everything's going to be proportional to gamma ij. We get an A double dot A here, and then we minus 3 A double dot A's there, give us minus 2 A double dot A. And then one more factor of, oh, I was missing a 2 here when I wrote this down. That's 2 from above. Is that right? Yeah, there's a 2 here. Okay. So that's minus A dot squared gamma ij. And this equals 8 pi g t ij. So now we can just take the trace of both sides. This piece gives 3a squared times the sum over x of all of the pressures of everything. And on the left-hand side, we just get a factor of 3 multiplying all of this other stuff. So this gives us a final equation, A double dot A plus 1/2 A dot over A squared plus kappa over A squared equals minus 4 pi g over 3 times the sum, wait, let's see, I have an extra factor of 3. No, that's right. At this point, this is minus 4 pi g times the sum over x times all the pressure. Dumb question, how do you define the pressure? Not a dumb question, so I can define it in 2 ways. One is I can define it as being the result of taking this, the trace of the spatial part of the trace of the pressure, sorry, the stress energy tensor. And that's one way of defining what the pressure is. I can also compute it using thermodynamic equations, which we'll actually do shortly. But for now, for our purposes here, yeah, I guess that you can think of it a couple ways. If you do this trace of it, yeah, I guess that question is maybe more about like, how do you define the components of the stress energy tensor? And I didn't really go into that in much detail, but if you ask what this object is, Tij or T mu nu, it's like the energy flux in direction I, the energy flux in direction I on a surface perpendicular to direction J. And that same quantity will also tell you that this this summing over this trace should be the net pressure and a little volume around the point. Does that answer your question? You can think it's just the same as the usual definition of pressure of like the average force on a little surface, the average force per area on a little surface. Okay. So this is written in this way for you to notice that this piece here looks just like the piece from the Friedmann equation up here. And so that means it's equal to 8 pi g over 3 times the sum over the energy densities of all the stuff. And so usually the Gij equation is mixed with the G00 equation to produce, usually we take the Gij equation, which is here, and use the results of the G00 equation here to plug it in to create an equation called the acceleration equation. Okay, and good. Okay, so this is called the acceleration equation. And then there is a third equation that we can use. And there's a third equation we can get from the continuity equation, which I wrote down earlier, which will help us solve the whole system. So finally, we have the continuity equation. And if we take the, actually, let me write it in components. Take the nu equals 0 equation, then we get d0, t 0, 0, plus di, ti 0, and then plus the Christoffel symbols, which we need, mu, mu, alpha, t alpha 0, plus, oops, wait, that's right, let me make sure I'm not missing something. Shouldn't we consider the cosmological constant? It doesn't matter. So you can either consider the cosmological constant is a modification to, you can think of the cosmological constant the cosmological constant is a modification to Einstein's equation here, where you add another term, which can be added to the side, which is like, which is proportional to the metric. So it's plus GAB times some constant. But that's completely, that you could write it by modifying this here, or you can just shove some term into TAB, which has a TAB, which is just proportional to the metric again, and you get the same answer. So we haven't, this is so far completely general. Sorry, let me rewrite this and make sure I'm not missing any terms. Okay, so alpha, but then we also have mu 0, alpha t mu alpha. And I think that's right. Good, that's all the terms is equal to 0. So by the assumption of homogeneity and isotropy, this term vanishes. There's no off-diagonal terms in the coordinate system where the metric looks FRW. And so that means that this looks like D0 T0 0 plus gamma mu mu 0 T0 0 plus gamma 0 0 0 T0 0 plus gamma 0 ij T ij is equal to 0. This Christoffel symbol vanishes. And this one, going back to our notes, should be 3. It's only the case where mu equals I equals j is non-vanishing, and that gives us a 3h. And this one gives us an a dot a gamma ij. So this a dot a gamma ij times Tij is equal to from above is equal to a dot over a times 3 times the pressure again, for the sums of all the pressures. So the equation that we get with T0 0 equals also the sums of all the energy densities. The equation we get is d by dt of, let me call this rho total and this p total, rho total plus 3h rho total plus p total equals 0. Okay, and this can also be rewritten as d log a is equal to minus 3 rho plus p. So okay, so note this is always true no matter what. So this is our generalized energy conservation in some sense. For total energy density and total pressure. So you could have like a bunch of non-relativistic particles that are expanding, and they all decay into massless particles, and this equation will hold through that transition. So it's always true as long as you sum over all of the matter. If there's no interactions between different stuff, and I'm saying stuff as opposed to species, so we can talk about scalar fields, or I mean, we can talk about anything. We can call it species, but between different, say, species, then this equation holds individual for each species separately. Okay, so this written in either form is our third equation, and I will call this the trio of Cosmology 101 equations, the fundamental equations for cosmology are h squared plus kappa over a squared equals 8 pi g over 3 rho, where this is now going to be total. The acceleration equation and continuity equation. Yeah, 1 second. Okay, so for a species with self-interactions, yeah, that's fine. A species with self-interactions will still continue to satisfy, if there's no interactions between the species, even if it has self-interactions, it still continues to satisfy this. It's always the case that this is satisfied for total energy density, total pressure of all constituents. And that includes a species that has frequent scatterings or something like that. In some sense, this is coming back to a point that I made yesterday, that from the point of view so far, in particular of cosmology and the very large scale behavior of the universe, the overall expansion, rate, acceleration, expansion history, there's really the universe and Einstein's equations do not care about whether something's self-interacting or not. So that the particular processes that might be happening that give gas pressure, for instance, scatterings, or how it's produced, just doesn't enter into any of these equations. Okay, I want to add one more equation to this. So this is the trio of equations that describe how the universe expands in terms of the stuff that's present. What is the meaning of the sum? The sum over x means different, rho x means species x. Okay, sorry, two. So sum over x means species x. So just x is, the self-interaction of some species will affect its distribution, but the equation still holds. Yeah, that's fine. But the expansion rate, if I want to compute, if I want to know the expansion history of the universe, I only need to know these equations. And in fact, any two of these equations is sufficient. I don't even need all three. So what this says is that the expansion history of the universe only cares about the total energy density and the total pressure. It doesn't care about whether that energy density is produced by a thermal distribution or a bunch of particles with like one particular value of the momentum that sums up to give the exact thermal distribution. The expansion history of the universe doesn't, Einstein's equations can't distinguish that. These three equations are not independent. So only need two of 1, 2, and 3. But in different circumstances, it's convenient to use different ones. I mean, you need some way of relating the. I mean, yeah. That if you could check that by taking. You can take, for instance, you can take the derivative. So this equation only depends on the first derivative of a dot. If I take the time derivative of this equation again, then I'll get an a double dot here, but then I'll have a rho dot on this side, and then I can plug in this continuity equation, and I'll get this equation back, for instance. But yeah, if I'm relating these two, for instance, the curvature only shows up in this one. So this would show up as like an integration constant trying to get this equation back. Okay, so I want to add another thing to consider for this case is the equation of motion for individual particles traveling through this expanding universe. And that's the geodesic equation. And it looks like this. And now we can define a momentum, which I'm going to call capital P, which will be potentially confused with pressure from above, but it will have an index, so that will hopefully help us keep track of it. And this is like the canonical momentum that you would find if you look at the Lagrangian that produces this equation of motion. You would say that this is the canonical momentum, and this is the momentum that satisfies the usual relation of like this. And we would say that P0 is the energy. And the momentum, the magnitude of the momentum we'd measure measured by a co-moving observer. So a co-moving observer is one that has adjusted their coordinates to look like the FRW metric. Would be, I'll call this little p squared, and this would be Gij, Pi, Pj, which is a squared gamma ij, Pi, Pj. Okay. So, and you can think of this equation as helping to define lambda. So if this is a massive particle, then lambda is tau over m, where tau is the proper time, and if it's massless, then you just define lambda in terms of this equation. So okay, so now taking the geodesic equation, we can rewrite that using these definitions. We can rewrite this as dp mu d lambda plus gamma mu nu rho p nu p rho equals 0. And since p0 equals dt d lambda, if we divide both sides by p0, we get dp mu dt plus gamma mu nu rho p nu p rho over p0 equals to 0. And then let's take the mu equals 0 equation, and this will give dE dt, change in energy, is equal to if mu is equal to 0, we only had one non-vanishing Christoffel symbol, and that's the one where that's gamma 0 ij. So we would have gamma 0 ij, and this was a dot a gamma ij. So we get a dot a gamma ij pi pj over p0. And this stuff can be rewritten in terms of our definition right here of the magnitude of the momentum measured by a co-moving observer and the energy to give a dot over a p squared over e. So we get one equation like this. And using the relation above that defines the last thing, sorry. So this is the momentum that satisfies this equation. And with this definition of E and P, then you have that E squared is equal to P squared plus M squared. And that lets you rewrite this as dp dt plus a dot over a p is equal to 0, which has the solution p p goes like 1 over a. So the momentum measured by a co-moving observer redshifts, we say. And this is true for all particles, all non-interacting particles, let me say, if they're scattering off stuff. So all particles traveling on geodesics are ones that are not subject to any other external forces. But it's true for both massive particles and massless particles. Okay. Are there any questions about that? Okay. The question is, can you approximate the continuity equation as being separate for individual things if the interactions between them are small? So yeah, so that's absolutely right. And so I said, if there's no interactions, but is there ever really no interactions? Maybe, but most things just have infrequent interactions. And then the question is, well, how frequent do the interactions have to be for us to care about them? And the answer is that you should usually, the thing that you usually care about is the interaction timescale compared to the expansion timescale. So you would say that things are interacting frequently if their scattering rate is high compared to the expansion rate, and vice versa. If the expansion rate is large compared to the expansion timescale, then for the practical purposes of this equation, in every expansion time, there's no interactions, and so you could treat them separately. And we'll do an example of that hopefully shortly today, but maybe tomorrow. Okay. Okay, so now let's solve these equations for some example stuff, some examples. So the first example is that the universe is full of you hear, okay. Only contains particles with no thermal velocities, or very, very, very small thermal velocities in comparison to their energy density. So this is sometimes called dust, or this is true for cold dark matter. But with negligible velocities, so E is approximately just equal to the rest mass. For this stuff, then P is equal to 0, or P over rho, I should say. You can be careful. So that means that our equation, the continuity equation, just gives that d rho d log A equals -3 rho. So rho goes like A to the -3. And that's the energy density is just the rest mass of the stuff, and it dilutes with the volume as the universe expands. Another example stuff is what cosmologists call radiation, where we mean relativistic particles. They can have mass, but we need P is much, much bigger than M for most of these particles. And then, oops, the pressure is equal to rho over 3. And so the continuity equation gives rho goes like a to the minus 4. And you can also think of this as, so the number density of all the particles drops off with the volume, 1 over a cubed, but then the energy of each individual particle also decreases as the universe expands. So that makes this 1 over a to the 4th. Actually, let me do this. Let's take each one of these and then let's compute how the universe expands for each one of these. So if we plug that into this equation, if the universe was only full of this stuff, then you would have the equation h squared is equal to 8 pi g. This is the pressure for a relativistic, like a relativistic gas. This we can compute this in a second again from the distribution, but this is just a result from like statistical mechanics. Oh, sorry. Did I do this? Did I? No, I think that's right. P is equal to the third row. Okay. H squared is equal to. Okay, so in a universe that contains only dust, let me put flat here. We can consider curvature separately, but all of these examples, 8 pi g over 3, and then we have rho of a, and this is just proportional to a to the minus 3. So that means that dA dt is proportional to a to the minus 3 halves times one more factor of a from this side. Just rewrite it like this. Sorry. Okay. So that gives that a to the minus 1/2. So this will give a is proportional to t to the 2/3. T is proportional to a to the 3 halves for the expansion rate, and then h is equal to 2 over 3t. Helpful to know. In the radiation case, we'll have h squared again, 8 pi g over 3, but now this is proportional to a to the minus 4. So we get 1 over a dA dt is proportional to a to the minus 2. So that gives a squared is proportional to t, or a is proportional to t to the 1/2. If we want to, we could consider curvature to be term to be stuff with rho proportional to 1 over a squared. So you could consider an empty universe and just move this piece to the other side. And then this would look like the energy density and curvature dilutes as 1 over a squared. And then you could solve for this. And this one gives a is proportional to W. Sorry, I think I have to do it. I didn't plan on writing this one. I forgot how it scales offhand. So then we get 1 over a dA dt is proportional to a to the minus 1. That's not right. Oh yeah, okay. So then we'd have, then we just have a is proportional to t. Okay, and then the vacuum case, vacuum energy, or cosmological constant has P is equal to minus rho, which gives the equation that rho is constant. The heck is that? And so then h squared 8 pi g over 3 times rho goes like a constant, means that 1 over a dA dt equals a constant. And the solution to this is a of t is proportional to e to the ht. It's exponential. The general case, for something, everything doesn't have to be described by this, but for pressure equal to W times rho, where this is called the equation of state. If W is equal to a constant, then one will find that rho of A is proportional to A to the minus 3, 1 plus W. And for W not equal to minus 1, you find that A of t is proportional to t to the 2 over 3 times 1 plus W. And the special case of W equals minus 1, we already did up here, and that's exponential. Okay, so these are general cosmological solutions. So depending on what type of stuff is around, the universe expands differently. And it's clear that, you know, even if you could have multiple things around at any given time, as we think our universe does, right? We definitely have non-relativistic matter that's present in our universe, and the energy density of that drops off as a to the minus 3. And we also have relativistic particles, and the energy density of that drops off as a to the minus 4. Since these drop off at different rates in the past, there's some point in the past where this energy density in radiation will have exceeded the energy density in non-relativistic particles. And so the universe can go through phases of having a phase where the energy density is dominated by radiation. And to good approximation, the expansion rate scales like this. And then it expands and dilutes, cool. The energy density in relativistic particles drops faster than that in non-relativistic particles. It becomes matter dominated, and to good approximation, the expansion rate goes like t to the 2/3. If there was spatial curvature in our universe, we haven't found any. We might expect that to become important at some point. It dilutes even more slowly than the energy density in non-relativistic particles, but we haven't found any yet. We do seem to think that there is some vacuum energy or cosmological constant in our universe, which has an energy density that doesn't dilute at all. And so we are approaching a phase where the expansion is exponential. It's sort of midway between exponential and this t to the 2/3. And there's some approximate solution that interpolates between the two of those. So let's continue talking about our universe. So it has, we think, our universe is described to good approximation by all the stuff that we see. We have this Friedman equation. We haven't seen any curvature. We do see something like cold dark matter. We see baryonic matter, which cosmologists lump baryons and leptons all into baryon because the leptons that are present, like electrons, electrons are grouped with protons and neutrons because their mass is so small that they make a negligible contribution to this. So cosmologists are a little sloppy about what they mean by baryon. And they don't really just mean baryons. They mean they include electrons in there. We have neutrinos, we have photons, and we have a cosmological constant or vacuum energy density. So these scale like a to the -3 for most of the time. The neutrinos, energy density, scales like a to the -4 at early times. And then as the universe expands and cools and their temperature drops below the rest mass, it's going like a to the -3 today. This one goes like a to the -4 always, and this one is a constant. So some notation, we often rewrite this, define h naught is equal to h of a equals 1, the expansion rate today, and then rewrite the above equation as h squared equals 8, equals h naught squared times all of this stuff. So maybe there's other stuff that we don't know about. This quantity right here has the units of energy density. Sorry, units of 1 over energy density. And it's defined, it has a name, it's called the critical density today, where this, I'm putting this 0 means today. So why is that? Well, if the sum over all the energy densities divided by the critical density is equal to 1, then kappa is equal to 0 and the universe is spatially flat. So that, and in the above equation, I've already dropped this curvature term because we find no evidence of spatial curvature in our universe so far, but people keep looking for it, so you can keep it there. So it does seem to satisfy this. Some other definitions are the fractional energy densities in different stuff with respect to the critical density today. You can define these at any redshift. I'll define them at redshift 0. My notation is that they mean the ones at redshift 0. So you can this is just a convenient notation. One thing is that this depends on h naught, since the critical density depends on h naught. And h naught is not like a fundamental constant. Everything else in here, 8, pi, 3, those are like numbers, pi, and then g, which is a constant of nature. But h naught's not a constant of nature. It's just, it happens to be the expansion rate today, and it's something we have to go out and measure. And it's measured relatively well, but not perfectly. So there's a better way to characterize the physical densities. By, oh, I forgot to define something. So h naught is equal to h at a equals 1. And we often, instead of using h naught, we define this a parameter called little h, so that h naught is 100 kilometers per second per megaparsec times little h. So you could use this as a measure of the expansion rate today, or you could use this dimensionless thing defined in this way as a measure of the expansion rate today. And then the physical densities are better characterized by omega x equals little omega x equals big omega x times h squared. And you'll see this is rho x and then divided by stuff that is just constants. So this is a better measure of the physical densities because it's just the actual density of the stuff divided by some constants. It doesn't depend on when we're doing the measurement, nor how accurately we measure the local expansion rate. And let's see. Okay, these are cosmologist units. A megaparsec up here. is a convenient unit in cosmology because the range of scales we consider tends to be like, you know, tenths of megaparsecs to like thousands of them. So it's a nice unit. A megaparsec is 3.086 times 10 to the 10 meters. And my mnemonic device for this is that this is approximately 30 petameters. That's how I remember how much that is. Okay, so in our universe, we have all this stuff, and the total energy density varies throughout cosmic history. And we have all of these different things. And I guess this is fun. I can use colors, which I didn't use. So we have photons, and their energy density dilutes as 1 over a to the 4th. And we have neutrinos. I like to make neutrinos brown. And their energy density dilutes as 1 over a to the 4th. And then at some point, they become non-relativistic. Let me make this line lower. Oops, I didn't mean to erase the. Okay. I'm not good at this. Okay, 1 over a to the 4th, and then they go like 1 over a cubed. So here we have rho gamma photons. I can have other stuff in here too. We can have other relativistic particles that are important in the earlier universe. We have CDM and baryons, and their energy density dilutes as 1 over a cubed. And then we have this bizarro vacuum energy, which seems to be constant, but we keep checking. And let me add some of these epochs on here. So here, the time when these guys cross is called matter radiation equality, or often just equality for short. This time when neutrinos become non-relativistic, I'll call A and R for neutrinos. And then this time when the matter density, when the energy density and cosmological constant takes over, I'll call A lambda. And we seem to live here, pretty close after A lambda. So if A today is equal to 1, A lambda is like 0.7. A and R, we don't really know, but it's bigger than 0.034. And we can compute that in a moment. There'll be an exercise. Oh, thanks. I wrote parsec. Sorry. This is just a parsec, not a megaparsec. A megaparsec. Thank you. Yeah. What is this is 16. Why is that not visible? Okay, so that's 1 parsec, which makes it easier to remember the mnemonic of petameters. And A equality is about 1 over 3,300. So, okay, so that's our universe at relatively late times. And of course, we can have other particles will exist besides, you know, I didn't put electrons on here because I grouped them with baryons at late times, but actually at early times, they're relativistic and they contribute to the relativistic energy density. And there are other, as the universe heats up, more and more particles come into thermal equilibrium or can be produced. So there's, muons and everything else. At sufficiently high temperatures, all the quarks and everything are in thermal equilibrium. So this, now let's see, okay. I want to say next. So sometimes just some more notation. So at late times, where I mean, say Z less than 10 or so. Oh yeah, I meant to say about this as well, what observations we have that probe different things. So we'll talk about this in more detail. The cosmic microwave background can actually probe this whole era, but the CMB is formed, or the CMB photons are released at a time. This is getting a little bit messy. So let me make a new chart over here where I say the equality. And this is all on a scale where A today is 1. Okay, so the CMB can probe, actually has some information about all of cosmic history, but what's called the primary CMB is emitted at this time. So CMB is great for probing these early eras and above, but because some CMB photons scatter on the way to reach us, they get gravitationally lensed and so on, we get a little bit of information about late times. Data on things like galaxy surveys and type 1a supernova are all at relatively late times. Okay, the question is, can we have A and R earlier, given that we don't know the neutrino's mass? And the answer is no, we have a lower bound on it because we have a lower bound on the mass from oscillation data. So the massive, that there's at least, given the neutrino oscillation data, at least one mass state has a mass of about 0.048 eV or larger, and that gives a lower bound on the time that it could have become non-relativistic. Sorry, that gives an upper, that gives a lower bound. Sorry, do I have this equality in the wrong way? So, yeah, that gives a lower bound. So it could have become non-relativistic. Yeah, sorry, I have this inequality the wrong way. It could have become non-relativistic earlier. Actually, I can't, let's see. So there's a lower bound on the neutrino mass from oscillation data, and that sets on, there's a lower bound that the mass is at least like 0.05 eV. If it was exactly that mass, it would have become non-relativistic around a redshift of like 200. If it had a higher mass, it would have become non-relativistic earlier. But from cosmology, we have constraints on the time at which it became non-relativistic. So there's a lower and an upper bound here. And actually, I just made a note, and I can't remember. This note is using this bound here is using, if it's a lower bound, this is using the cosmology data, but there's actually, so there's two bounds on either side. So we can come back to this. So we can write this like this. ANR is So ANR is roughly temperature of the neutrinos, which we'll do as an exercise, divided by the mass. And given the current constraints, this gives two bounds, which are roughly, so T nu 1.7 times 10 to the minus 4 eV. And then the lower bound from, well, I'm just gonna, in the interest of time, I'll just write this all over these two things. So ANR has to be, the cosmology upper bound gives us lower bound here, which is somewhere like 0.07 EV-ish. And then the oscillation data says at least one eigenstate, somewhere like that. So yeah, so this side is from these colors. And this side is from oscillation data. So that's fun. There's a lower, whenever there's a lower bound and an upper bound, at some point, the oscillation data will not change. Even if that improves, that's not going to change this overall limit, but the cosmology constraints will keep getting better. And so then this will be pinned down. Okay. So for the late time measurements, oops, let's go back to using black. So this means stuff that people see in galaxy surveys, 21 centimeter, lensing, whenever anyone's talking about BAO measurements, which come from galaxy surveys, clusters of galaxies, oh yeah, and then supernova 1A. Then neutrinos are totally non-relativistic, and the Hubble parameter, the Hubble equation is written in this way. And these things are collectively called omega, wrong omega. Well, so that's, so all the stuff that's non-relativistic today is grouped here. Even though when you're looking at the CMB, neutrinos were relativistic at the time of the primary CMB. So the stuff that's non-relativistic in the CMB is just cold dark matter and baryons, but the stuff that's non-relativistic at late times includes neutrinos. So when people talk about the 6-parameter cosmological model, this equation includes 3 of the 6 parameters. And they are.
If you've lost track of time, you're a little bit over.
Oh, okay, sorry.
As a reminder.
Okay, I had lost track of time. Let me, I'm a little bit over. Let me make 2 comments. So this equation includes 3 of the 6 cosmological parameters, and we'll go on to talk about the others. And omega gamma is measured. Of course, this is like a parameter, but this is measured exquisitely from direct measurements. It's overwhelmingly dominated by CMB. So even though, you know, if you wanted to tell some space alien about the contents of our universe who lives in some parallel universe, you need to tell them this. It's not considered a parameter because it's known so well. And then omega nu is predicted from omega gamma, and plus you get these limits from oscillation data. So if you assume a minimal mass normal hierarchy or inverted hierarchy, then you get a firm prediction for omega nu. And we'll do that next time. Sorry about going over. Thanks.
Yeah,
Yeah, that's right. The question is, we ignore the energy density for radiation in H above because it's so small at that time. So today, today omega gamma is like 10 to the minus 5. And the other omegas, this one is approximately 0.3, and this one is approximately 0.7. So that's negligible. At late times. I'm just pointing this out so that you know what it means by omega matter.
So any last minute questions? Otherwise, we virtually thank the speaker again, and we'll see you again on Thursday.
Okay.
And just as a reminder, there is the last lecture today. It's in about 15 to 20 minutes. So I hope to see everybody take this opportunity to get up and stretch and maybe drink some water or something like that. And we're almost there. Well, thank you.
Okay. Thanks, everyone. Thanks for your virtual. Thanks. It's nice to see people are out there.